Hello everyone, welcome to channel Statistica Hub. In the previous lecture of basis and dimension, we have studied our last theorem, basis and dimension. We have studied the last theorem as that if I have a V, which is our vector space, and the dimension of this vector space V is n, then any n plus 1 or more vectors in V are linearly dependent. Okay. The second statement is that any linearly independent set S, which is equals to u1, u2 to un with un with n elements is a basis of V. And the third statement is that any spanning set T equals to V1, V2 to Vn, where all these vectors belong to the vector space V with n elements is a basis of V. Okay. So I have a vector space V which has dimension n. Then it means that I have n linearly independent vectors. So if I add this is my set, it has n linearly independent vectors. Then if I add one more vector which is n plus 1 in this set, then this vector would be linearly dependent. Okay. Next statement is that any linearly independent set which has n elements, the set of vectors which has n elements, linearly independent set of n elements, is form the basis of V. Okay, and any spanning set which has n elements also form the basis of V, because we have the dimension n here. Okay, now let's see another theorem, which is as suppose there is a set S of vectors u1, u2 to un which spans the vector space V. Okay, so if this set of vectors spans the vector space V, then every vector of V, let's say V, which belongs to the vector space V, every vector of V can be written in the linear combination of these vectors, which is V equals to alpha 1 u1 plus alpha 2 u2 to alpha m un. Okay, now from this we can say that any maximum number of linearly independent vectors in S form a basis of V. Okay. Now in this I am saying that I have this set S, which is the generating set of vector space V. Or we can say that this is the set which spans the vector space V, which generates the vector space V. Now from this set there are some elements which are linearly independent, there are some vectors which are linearly dependent, and from this set if I take out all the vectors which are linearly independent, okay, all the vectors which are linearly independent, then these vectors would form the basis, because from the definition of basis, the vectors which are linearly independent and generates the whole vector space are basis. Okay, so if I say that the dimension of vector space V is n, then the number of vectors in the spanning set are m. Okay, then the possible case form here are that m can be less than n, m is equal to n, and m is greater than n. And if I see the first case, which is m is greater than n, m is less than n. Okay, so from this you can see that the spanning set has m elements, and the dimension has n elements. Okay, now but this is not the possible case, because spanning set can't have number of vectors less than dimension. Spanning set can't have number of vectors less than dimension n. because it is the set. This spanning set is the set. From this we take out our linearly independent vectors. We take out our basis vectors. Okay, and this basis, that this the number of basis vectors that I mentioned. So we can't have m less than n. Okay, and the second case where m is equals to n, that the dimension, that the basis vector n is basis vectors are, number of basis vectors are n, and the number of vectors in our spanning set are also n. Okay, these both are equal. Then in this case all vectors of v can be expressed as linear combinations of ui's. All vectors of v can be expressed in linear combination of ui's. In linear combination of ui's. Okay, so in this case we have m vectors which are spanning v vector space, and we have, as m is equals to n, then we have m vectors which are linearly independent. So in this case, these will form the basis. These will form basis. Okay, and we have another case when m is greater than n. M is greater than n when the number of vectors in the spanning set are greater than the number of linearly independent set. Okay, in this case what we do, we'll just remove all those dependent vectors. Okay, as I have said that I have this set which has some linearly independent vectors and some linearly dependent vectors, then we'll just take out all the vectors which are linearly independent, and as our dimension is n, we will have maximum number of n linearly independent vectors. Then we'll just remove all those vectors which are linearly dependent, and take out all those vectors which are linearly dependent. Okay, so from this we got that any maximum number of linearly independent vectors in S will form the basis of V. Okay, now we can also state it as like that we can, if from this set S, okay, if from this S set at S I delete all the vectors which are linearly dependent, then the set of remaining vectors will form the basis, because it contains all the vectors which are linearly independent. These are similar statements. Okay, now there is one more thing, which is, let v be a vector space. We'll always take our vector space, we'll always be taking vector space on all over the things. Okay, let v be the vector space which has a finite dimension n. Okay, and this is the dimension here, and S is the set of vectors which is u1 u2 to ur. This is the set of vectors which is linearly independent vectors in V. What? Okay, this is the set of vectors which are linearly independent in V. Okay, in the previous theorem we have taken the vectors which generates the vector space V, and in this case we are taking the set of vectors which are linearly independent in V. Okay, now let's say we have the dimension n, then the possible case will be r is less than n, r equals to n. Okay, the set of vectors r, the number of vectors in this are r. Okay, and r is greater than n. Okay, when in the first case when r is less than n, then in this case, so we have dimension n. Okay, which means there has to be n linearly independent vectors, and in this vector space V, we have given r linearly independent vectors which are less than n, in the first case. Okay, so in this case we add by adding more vectors. We have to add n minus r vectors. By adding n minus r vectors, because we have to form the basis, and for the basis we should have n linearly independent vectors. Okay, so we'll add n minus r vectors more to this case, and when we have n linearly independent vectors when r equals to n, then in this case it will form the basis. There is no contradiction here, it will form basis. Okay, and the third case where r is greater than n, it is saying if the set of these vector r is greater than n, but I have said but we have n where this is our maximum number of linearly independent vectors in vector space V. Okay, so we can have only n linearly independent vectors. But if I have r greater than n, then it will be linearly dependent. We have studied this in the previous theorem. Okay, then it will be linearly independent. So from this we got that that this set S, this set of vectors S is a part of basis, is a part of basis of V vector space. That is, S can be extended, S can be extended to a basis of B, to a basis of V. Okay, so this is actually the extension theorem. You can also say that it is a extension theorem. Okay, now before studying these two important theorems which are as extension theorem, and there is one more which is deletion theorem. Deletion theorem. So we have just named them as extension theorem by adding linearly independent vectors for the basis, and deletion theorem the removing of linearly dependent vectors. Okay, okay, okay. So before studying them, let's just see an example. If I have this set of vectors S which is as 0 1 1 1 0 1 1 1 0, okay, which is basis of R cube, which is basis of R cube. Now I want to check whether it is actually a basis of R cube or not. Okay, for checking the basis, what are the two conditions? First, it should be linearly independent, and the second, it should span the whole vector space. Okay, it should span vector space. Here is R cube. Okay, so first let's check whether these are linearly independent. For linearly independent, we'll just for the constant, let's just take the scalars as Ci's. So C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3, where this is alpha 1, alpha 2 and alpha 3. Okay, which is equals to 0. Now for the scalar, for the linear independence, the value of the scalar should be 0. Okay, let's just find that out. 0 1 1 plus C2 1 0 1 plus C3 1 1 0 equals to 0. Now from this I got C1 plus C3 equals to 0, C1 plus C2 equals to 0, C2 plus C3 equals to 0. Okay, which gives me C1 equals to C2 equals to C3 equals to 0. So this set S is linearly independent. If I check for spanning, but here I can also easily see that I have the vector space of R cube, so it will have the dimension 3. Okay, it will have the dimension, and I have 3 linearly independent set of vectors, so this will form the basis. This will form the basis. So let's just check it in a proper way. Okay, so let I have a vector E which is A B C, and this set of vectors span by the vectors by the set of S. This vector which belong to the vector space V, sorry, here the vector space is R cube. Okay, and this vector is spanned by the set S. Okay, so it will be written in their linear combination, which is E equals to, for the scalars Ri's, R1 alpha 1 plus R2 alpha 2 plus R3 alpha 3, where E is A, B, C, and R1 alpha is R0 1 1 plus R2 1 0 1 plus R3, which is 1 1 0. Okay, now the corresponding equations to this are R2 plus R3 equals to A, R1 plus R3 equals to B, and R1 plus R2 equals to C. Okay, now let's just form these equations into the matrix. Like this will give 0 1 1 1 0 1 1 1 0. We'll just apply the Cramer rule here. We have studied the Cramer rule previously. So if I take the determinant of this, it will give me minus 1 and 0 minus 1 plus 1 plus 1 and 1 minus 8. Okay, this will give me 2. Okay, my determinant is 2, which is not equals to 0. So from the Cramer rule, I got that there exists a unique solution. There exists a unique solution for R1, R2, R3. So from this I got that the vector E which belong to the R cube, the vector space R cube is spanned by the set S, which has three vectors. So this spans the vector space. These vectors are linearly independent, so these will form the basis. These are forming the basis. Okay. Now let's see another thing, which is we have studied the dimension. Now let's see by an example. If I have the set S, which is S X Y Z W, which belong to the R's power 4. Okay, this is the vector space here. Okay, and the condition is that 2x plus y plus 3z plus w equals to 0. And there is another set T, which is x, y, z, w, where this is also belongs to R's power 4, and x plus 2y plus z plus 3w equals to 0. Okay, now these two are S and T are subspaces of vector space R's power 4. And I want to find the dimension of S intersection T. I want to find this. Okay. How will we do that? What is the S intersection T? S intersection T is that X, Y, Z, W belong to the vector space R's power 4 with the two conditions. First one is this, comma, second one is this. Okay. Now let's just solve these equations. Okay. So for this, let's say I have the vector E, which belong to this intersection. Let's say A, B, C, D is the corresponding elements of this vector, which belong to this intersection S intersection T. Which in this intersection we have to apply both these conditions. Okay. So let's say if this, so we can represent this E vector in these linear equations, in these conditions as not linear equations. 2a plus b plus 3c plus d equals to 0, and the other is a plus 2b plus c plus 3d equals to 0. Okay. Now let's just simplify this, multiplying this equation by 2. So this will give us 2a plus 4b plus 2c plus 6d equals to 0. Minus, and this will give us minus 3b plus c minus 5d equals to 0. And from this I got the value of c as 5d plus 3b. Okay. And by putting this value in this equation, I got a plus 2b plus 5d plus 3b plus 3d, which is equals to 0. Then I got a equals to minus 5b minus 8d. This is my A. Okay. Now my E vector is minus 5b minus 8d, comma b, comma 5d plus 3b, comma d. This is my E vector. Okay. Now let's just take out b from here. It will give me minus 5, 1, 3, 0 plus another vector d, which is minus 8, minus 8, 0, 5, 1 when I take out the d constant. Okay. So these are our basis vector. These are the basis vector for the S intersection T. Okay. So let's say this is alpha, this is beta. So this E spans the vector space spans the set spanned by the set S intersection T, and it has the basis alpha and beta, and the dimension of S intersection T would be 2, as it has two bases. Okay, so that's how we can find the dimension of the intersection of two subspaces. Okay, now let's see a dimension more clearly. If I say that the dimension of any vector space is n, what does it say? It say that the number of linearly independent vectors in the vector space V are n, which is maximum number of linearly independent vectors. Okay, and no generating set of V contains less than n vectors. Okay, generating set of V, no generating set of V contains less than n vectors. Okay, third statement is that every linearly set of n vectors in V is a basis of V. Every linearly independent set is a basis of V, which has n vectors. Okay, and the fourth is that every generating set of n vectors of V is also the basis of V. Basis of V. Okay. Now we have seen the extension and deletion of the vectors. Extension and deletion of the vectors. In the extension part, I have said that every linearly independent set in V, it can be extended to the basis of V. That every linearly independent set in V can be extended to basis of V. And in the deletion part, basis of V. And in the deletion part, I have said that every generating set of V contains a basis of V. Okay, a basis of V. Now let's just see these more clearly in the format of examples. It will give us clear understanding. Let's say if I have set S, which is of vectors as u1, u2, u3, u4, okay, which belongs to the r's power 4, and I have this condition as 2u1 plus u3 plus u4 equals to 0, u0, where I have x1, x2, x3, x4 as my generating set of S. This is my subspace. Okay, this is my generating set for this S. Okay, and the corresponding vectors x1 as 1 0 1 minus 3, x2 as 0 0 1 minus 1, x3 as 4 0 1 minus 9, x4 as 0 1 0 0. Okay, now we'll have to find the basis from this generating set of S, which is like I have this set which generates the whole subspace S. Now I want to find the basis from this um, set, from this generating set, like all the linearly independent vectors from this set. Okay, so if I see the vector x1 and x2, x1 and x2, so x1 and x2, you can say that these vectors are x1 and x2 are linearly independent, as one is not the scalar multiple of other. So x1 and x2 are linearly independent, x1 comma x2, which are li. And if there we take a seal the vector x3. Now let's just check whether this x3 belongs to the span of x1 comma x2, whether this x3 spanned by the vectors x1 and x3. So let's just see it. X3 equals to, for the scalar ci is c1 x1 plus c2, sorry, this is x2, c2 x2, which is x3 is 4 0 1 minus 9 equals to c1 1 0 1 minus 3 plus c2, which is 0 0 1 minus 1. Okay, let's just find the constant, which is c1 equals to 4, c1 plus c2 equals to 1, minus 3c1 minus c2 equals to minus 9, and this will give me c2 equals to minus 3, and this will also give me c2 equals to minus 3. Okay, so I have the constant as 4 and minus 3. So x3 can be represented as 4x1 minus 3x2, which is spanned by the vectors x1 and x3. So this belongs to L of x1 comma x2. So this is not linear independent because it is represented in their linear combination. Okay, now if I check the vector x4, let's just check whether this will be spanned by these vectors. Okay, so just check this. So 0 1 0 0, which is equals to, I am writing x4 as c1 x1 plus c2 x2 as I have done for x3. Okay, so c1 x1 vector is 1 0 1 minus 3 plus c2, which is 0 0 1 minus 1. From this I got that c1 equals to 0 and c1 plus c2 equals to 0, minus 3 c1 minus c2 equals to 0, and c1 equals to minus c2, and this c2 equals to minus 3 c1. From this I have got that c1 equals to 0, c1 equals to minus 3 c2, which is the contradiction. These are inconsistent equations. Okay, so x4 does not belong to L of x1 comma x2 because it is not spanned by these vectors. So this x4 is linearly independent. So from this I got that x1 x2 x4 x4 will form the basis and has the dimension 3, and has a dimension 3. Now let's just similarly look for the what did we say, extension theorem. Extension theorem, when we extend the number of linearly independent vectors for generating the vector space or for generating the basis. Okay, take the same subspace. While taking the same subspace, which is u1 u2 u3 u4. Okay, u4 which belongs to the r's power 4 and have the condition 2u1 plus u3 plus u4 equals to 0. Okay, and I have the basis vector as y1 y2 and y3. These are the three basis vectors that I have, which is y1 equals to 0 1 0 0, and y2 is 1 2 minus 1 minus 1, and another y3 as 1 0 0 minus 2, and there is one vector which is x1, which is 1 0 minus 1 minus 1, and this is a linear independent subset of S. All I know about this vector is this, that this is the linearly independent subset of S, and these are the basis vectors of S. Okay, now you can see that y1 vector, if I see the y1 vector is not the linear combination of this x1 vector. Okay, y1 vector is not the linear combination of this x1 vector. Okay, so y1 and x1 comma y1 are linearly independent in r's power 4. Now let's just check for y2 whether this y2 is linearly independent of these or this will form the linear combination. So y2, whether this will be spanned by these vectors x1 comma y1, which is as y2 equals to c1 x1 plus c2 x1 y1, which is y2 1 2 minus 1 minus 1 c1 1 0 minus 1 minus 1 plus c2 0 1 0 0. Okay, from this I got the constant as c1 equals to 1 and c2 equals to 2. Okay, c1 equals to 2 1, c2 equals to 2. So y2 can be represented as x1 plus 2 c2, so plus 2 y1, sorry, 2 y1. So this y2 can be represented in their linear combination. So this y2 is linearly dependent, it is not linearly independent. Now check for the vector y3. Y3, if we check for the vector y3, let's just replace this here. Then y3 can be represented as y3 equals to, we'll check for y3 as y3 belongs to this, whether y3 belongs to this x spanned by this vector x1 comma y1. So y3 equals to c1 x1 plus c2 y1. Okay, and the vector y3 is 1 0 0 and minus 2. From this I got the value of constant as c1 equals to 1, c2 equals to 0, minus of C1 equals to 0 and minus of C1 equals to minus 2, which are inconsistent, and these are contradiction statements, contradiction values of the scalars. Okay, so this y3 does not belong to the L of x1 comma y1. So this is linearly independent. So I got x1, y1, y3 are the corresponding and linearly independent bases of R's power 4, which has the dimension of 3. So like this, as I have done in the extension and the deletion process, like this we can generate the bases. We can have the bases. We can add the vectors and we can delete the vectors. Okay, now in the dimension case, there are some results. Okay, like this, if u be the subspace, if I have the subspace u, which is subspace, okay, and which has finite dimensional vector space n, we have finite dimensional vector space v, which has the dimension n. Okay, this is its dimension. Okay, that dimension of v equals to n. Then u is the subspace of this vector space v, then the dimension of u is less than equals to dimension of v, which is n, the dimension of u is less than equals to n, because it is its subspace. Second case is that if I have u and a w, which are two subspaces of finite dimensional vector space v over f. Okay, then the dimension of u plus w, the sum of these two subspaces will be dimension of u plus dimension of w minus dimension of u intersection w. Okay, if I have the u intersection w, the intersection of these two subspaces is phi, and the corresponding bases of these two subspaces, let's say alpha 1, alpha 2 to alpha m, be the basis of u, and beta 1, beta 2 to beta n. This is the basis of w. Then the basis for u plus w will be alpha 1 to alpha m, comma alpha 1 comma alpha 2 to alpha m, comma beta 1 beta 2 to beta m. This will be the basis for u1 plus u plus w if the intersection of these two subspaces is phi. Okay, now if I say that u and w are two subspaces which are complements of each other, complements of each other in the vector space v, then the dimension of v is equals to dimension of u plus dimension of w. Okay, now the other thing is that we are taking u and w be the two vector space, then u intersection w is also a subspace of vector space Vn. This is what we have studied earlier in the earlier lecture. Okay, and if I define the dimension of u intersection w, then this will be less than equals to minimum of dimension of u comma dimension of w. How? Let's see it like this. Okay, so this is, let's say, our vector space v. Okay, this is our vector space v over the field f. Okay, and this is my subspace u, and this is my subspace w, and this is the intersection of these two subspaces, which is u intersection w. Then when I say that the dimension of u intersection w is less than equals to minimum of dimension of u dimension of w, the result here, you can see from this graph that the maximum number of linearly independent vectors in u intersection w will be less than equals to maximum number of linearly independent vectors in the subspace u. Okay, what did I say? That maximum number of linearly independent in u intersection w will be less than equals to maximum number of linearly independent vectors in subspace U. That means that the dimension of U intersection W is less than equals to dimension of U. Okay. Similarly, the maximum number of linearly independent vectors in U intersection W are less than equals to the maximum number of linearly independent vectors in the whole subspace W. Similarly, dimension of U intersection W is less than equals to dimension of W. So from adding these two resultant, I will have that the dimension of U intersection W is less than equals to minimum of U dimension of U comma dimension of W. Okay. Now there is some results of you have studied this concept earlier of dimension and subspaces, that when I say that W is the subspace of of vector space V, and this vector space V has dimension n. Okay, and I have said that the dimension of this subspace W will be less than equals to n, the dimension of the whole vector space V. If 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 by any chance the dimension of W is equals to n, if the dimension of W is equals to n, this will be only possible if if W is equals to V. The only subspace, it means that the only subspace of V with dimension n is vector space V itself. What? Thus the only subspace of V with dimension n is vector space itself. Okay, when I say that the dimension of S, the dimension of S, any S and any T, dimension of S and dimension of T are equal, it does not show that S and T are equal. It doesn't depict that S and T are equal. It is important to note where S and T are subspaces. When I say that the dimension of two subspaces are equal, it doesn't mean that they are equal. Okay, but in this case, when W is the subspace of the vector space V, the dimension of W is equals to dimension of n only if that W equals to V. That the only subspace of V is the vector space itself, which has the dimension n. Okay. Now let's see it that W is the subspace of. Let's consider that the W is the subspace of R cube. Okay, this is our vector space R cube. Okay, and the dimension of this R cube is equals to 0. The dimension of the vector space is 3. Sorry, the dimension of this vector space is 3. Now the possible dimensions of this subspace can be 0, 1, 2, 3. This is the possible dimension for the subspace, because dimension of W has to be less than equals to n for the subspace of the subspace. Okay, so if I say that the dimension of W is equals to 0 of the for the vector space R cubed. Okay, if the dimension of W is equals to 0, it means that the dimension is only 0 when I have the point 0, which is a point, when W is equals to 0, which is a point. If I say that the dimension of W is equals to 1, which means dimension would be 1 if W is a line which is passing through the origin, then only the dimension of W is equals to 1. And if the dimension of W is equals to 2, then W is a plane. W is a plane passing the origin. Okay, and if the dimension of W is equals to 3, then dimension of W is equals to 3, then the W is the entire vector space. That is, W is the vector space V itself. We have seen this here. That dimension of W is equals to n when the W is equals to V. Okay, so this is what we have done in the concept of basis and dimension. Okay, thank you.